Hi, this is Jipeng coming from the University of Electronic Science and Technology of China. I am going to present our teacher-student networks with multiple decoders, a novel method for solving math word problems. Typically, a math word problem is composed of a problem description text, a solution expression and a final answer. An example is shown in the figure below. With such training examples, math word problem solvers should have two objectives to optimize: the generation loss of answer and the loss of solution generation. Nevertheless, most existing approaches use only the latter objective. In specific, these methods are based on the deep generative network composed by encoder-decoder architecture. The encoder encodes the problem text into latent embedding, and later these latent embeddings are fed into the decoder to generate the solution generation. This is similar to translating problem text into equations, which share the manner with machine translation and speech recognition. As is shown here, they deploy a single decoder and fit to the only solution expression given on datasets. It is, therefore, hard for them to generate diverse but equivalent solution expressions, limiting the generalization ability to various cases. More importantly, as there may exist multiple solution expressions and only one correct answer, this solution generation objective tends to give wrong penalty to correct solutions which are different from annotation 1. In order to address the limitations of the previous training methods, we suggest to consider these 2 points. First, how to regularize the training procedure so that the training can be guided under a better goal. Second, how to increase the diversity of generation. So, we proposed a TSNMD method. The key modifications are these 2 items. First, we propose to use teacher-student learning, which is also known as knowledge distillation, to help regularize the training procedure. We pre-train the teacher network to guide the learning behavior of the student network with the same training data. The intuition is that the teacher model observed through all solutions, including those with equivalent solution expressions under mathematical laws. Therefore, it gains the knowledge of regularizing the learning behaviors of the student network. More intuitively, when a student predicts an equivalent solution expression to the ground truth but causes an undesirable loss, the teacher network will help to amend this mistake by giving soft labels. Second, in order to encourage high-diversity predictions, that is, solution expressions, from the student network, we use multiple decoders. More specifically, one decoder behaves in the same manner as the previous model and the other one, which shares the structure with the former decoder, has its input embedding perturbed by a Gaussian noise. Besides, we added a diversity regularization item and separate beam search to encourage different decoders to generate different results. It is worth noticing that the solver can only output one solution expression. Therefore, we vote to get the output solution expression according to the prediction score given by different decoders. Here is the overview of our model architecture. We conduct experiments in Math23K and MAWPS. For Math23K, we evaluated in both training test division and 5-fold cross-validation manner. We can observe from the table below that our model outperforms all the previous methods in all settings. Another important experiment is to investigate the accuracy of solution expression prediction. More accurately, if the predicted solution expression exactly matches the annotated solution, we consider it a positive example. Here, we can compute the number of alternative solutions that each model can provide, which can partly tell the degree of diversity of a model. It can be observed that the accuracy of solution expression generation is lower than the final accuracy of problem solving. This reflects that these MWP solvers have spontaneously learned to adapt to the situation that a certain problem may have multiple solutions. In summary, we propose a novel approach: teacher-student networks with multiple decoders to tackle the MWP problems. The key components in our approach, that is, teacher-student regularization and multiple decoders in the student network, are validated to be of high effectiveness. The new state-of-the-art results are achieved on the Math23K and MAWPS benchmarks. Furthermore, our approach is easy to plug in other MWP solvers. Many thanks to your attention. Do let me know if you have some other questions.